Question number 9. What happens at a boundary? Describe the behavior of mechanical waves at boundaries, reflection and refraction. Now, a boundary is where a wave moves from one medium is a material, into another. For example, from a thick into a thin spring. When a wave reaches a boundary, two things can happen. You can pause and copy this. There are two things can happen. The first one, some of the wave continues into the new medium, that is called transmitted wave. Now you can see here is one spring, here is another spring. Two different springs are connected here. At this point we call a boundary. Now here we create a pulse. It is an incident wave, and this incident wave is moving to the another spring. It is a transmitted wave. Okay. Next, some of the wave bounces back as a reflected wave, and at the boundary, some wave is transmitted, some wave is bounced back. It is called the reflected. So you can see here the wave which is following to the right side is the transmitted, and bouncing back is the reflected. Reflection of waves. Reflection is when a wave bounces back from a boundary. It is upright or inverted. This depends on whether the boundary acts like a fixed or free end. If the boundary is a fixed end, how do we know? The boundary cannot move. If the boundary cannot move, and it is called the fixed end. Example, a rope tied tightly to a wall, it is a fixed end. If you tied it tightly at one end, it is a fixed end. The reflected wave comes back inverted. If the end is fixed, the bouncing the bouncing back wave is inverted, which means the up pulse becomes down, the down pulse become up. It is called inverted. There is a rule. Reflection from a fixed end is always inverted. Next, free end. The boundary can move freely. Now you can see the one end is fixed, not fixed, it is free end. You can see it is attached with a ring. If you apply a pulse, this ring can move freely up and down. It is not fixed. Okay, a rope tied to a loose ring that can slide up and down. The reflected wave comes back upright. Now you can see incident wave is up, the reflected wave is also up. So it is, the direction doesn't change, it is upright. Same like, the direction is same like incident wave. What is the rule? Reflection from a free end is equal to upright wave. C. Transmission and speed changes. When the wave enters a new medium, which means thick spring to the thin, or thin spring to thick. If the medium is stiff or light, travels faster. It's very important. If it is a stiffer spring, the wave travels faster, the speed is higher. Also, the lighter spring means the mass of the spring is less, the speed is more. Next point, if the medium is loose and heavy, then the speed is slow, wave travels slower. The shape stays upright when it crosses into the next medium. And we have a summary. At a boundary, part of the wave is transmitted and part is reflected. At the fixed end, reflected wave is inverted. At the free end, reflected wave is upright. When a wave enters a new medium, its speed changes, and that is called refraction. Again, the fixed end, reflected wave is inverted. At the free end, reflected wave is upright. Heavy spring, wave speed is slow. Light spring, wave speed is faster. The wave from thin to thick. Thin spring is a light, thick spring is heavy. And the boundary acts like a fixed end. If the spring is connected, thin and thick, the boundary is acting as a fixed end. If it is a fixed end and the reflected wave is inverted and transmitted wave is upright, you can copy and you can pause and copy this. Now, wave from thick to thin, heavy spring to the light spring if the wave is traveling, and the boundary is acting like free end. The reflected wave upright because it is acting as a free end. If the boundary is acting as a free end, the reflected wave, transmitted wave is always upright. And the transmitted wave is faster because the wave is traveling through the thin spring, so it is faster. The next question, principle of superposition. You can pause it and you can copy this. It is just a definition. State the principle of the superposition. When two or more waves meet, the total displacement of the medium is the algebraic sum of the displacement of each wave. Waves do not affect each other permanently. They pass through each other unchanged. Applying superposition, where constructive interference, waves meet with displacement in same direction. Amplitudes add bigger waveforms. A point of maximum displacement is called antinode. Destructive interference, wave meet with opposite displacement. Amplitudes subtract. Smaller or zero displacement. A point of zero displacement is called a node. You can see example, the constructive interference. You can see here is a crust and the crust. When these two crusts are meeting, they construct the wave. Now here is 1 centimeter, here is 1 centimeter. When they join together, it becomes 2 centimeter. And destructive interference, you can see here is a crust and it is interfering with the trough. When one unit of crust join with one unit of trough and they become 1 minus 1, 0. So same happens here, the crust and trough 0 and crust and trough 0 and here trough and crust 0. So you connect all the zeros is a straight line, horizontal line, 0. That is a destructive interference. Same here, crust 1 unit, here crust 1 unit, they join become 2 unit of crust. The trough 1 unit and trough 1 unit, when these two join become 2 unit of trough. Here you can see 1 crust and 1 trough, 1 unit, 1 minus 1, 0, cancel, and 1 trough, 1 crust, 1 minus 1, 0. So destructive interference. Okay, same here you can see one pulse is moving to the right, another pulse moving to the left. This crust pulse, here is also crust. When they meet, they become a double. It become means 1 unit, 2 unit becomes 2 units of crust. And later, it's a momentarily they join. The constructive interference is momentarily formed, and again the pulse trends are moving to the left, going to the left, and the pulse which is moving to the right is continuous to the right. Destructive interference, you can see here is a crust and one trough. They are going to join. When they join, they cancel each other and there is no pulse. It's a 0. displacement, and it is the node, it creates the node destructive interference, and later this left trough is follows to the left and the right crest follows to the right. Next question, formation of a standing wave. Standing wave, and we have a just we are describing it. You can pause and you can copy it down, and I can read it for you if you have any doubt with my handwriting. When a wave travels along a string and is reflected at the end, it meets the incoming wave. If the vibration frequency is such that the incident and reflected waves overlap perfectly, they interfere with each other. The pattern looks like the wave is not moving. This is a standing wave. Now we described the standing wave. The next part, we are describing nodes. A point on the string that never moves. Zero displacement. Nodes form where the incident and reflected waves cancel each other completely. Destructive interference. The ends of fixed string are always nodes. The ends of a fixed string are always nodes. Antinodes. A point on the string with maximum displacement. Antinodes form where the incident and reflected waves add up. Constructive interference. They appear halfway between two nodes. These 2 points, nodes, and halfway in between the nodes is the antinodes. This is one segment. Now I'm going to draw two segments. So if you increase one segment, you are increasing one node and one antinode. Before it was two nodes, one antinodes. Now you increase one node and you increase another antinode. So 2 plus 1, 3 nodes you can see, and 1 plus 1, 2 antinodes you can see. As you are increasing one full segment, this is a one segment. Here we have two segments. As you are increasing one segment, you are increasing one node and one antinode. Frequency and patterns. At the lowest frequency, one antinode forms in the middle with nodes at both ends. When frequency is doubled, one extra node and one extra antinode appear, as I discussed before. Now here is a frequency of one segment. Here we have two nodes, one antinodes. Now let's say it is 100 Hertz. Now we have two segments, which means double the frequency, 200 Hertz. When there is a 200 Hertz, now you can see there are three nodes and two antinodes. So as you double the frequency, you are increasing one node and one antinode. Higher the frequencies produce more nodes and more antinodes. Next question. Representation of waves in two dimensions. In two dimensions, waves spread out in all directions from a source. Now you have a source, a light source. From this light source, the light is spreading out in all the directions. They are shown using wavefronts, lines or circle. We have the plane wavefront and we have the circular wavefront. Straight wavefront show plane waves. Straight wavefront show plane waves, and circular wavefront shows a point source. If you have a point source, which means a bulb, a small bulb, it is a point source, it will create a circular wavefront. Spacing between wavefront shows wavelength. Now we have the plane wavefront. The space between the two wavefront is a lambda wavelength. Same like circular wave. spacing between the two circular waves is also